Hello everyone, welcome to Excel, Python and AI. I'm excited to be here at the 2025 Actuarial Technology Summit. We are going to talk about transformation, not just of our tools, but of our mindset. We are going to explore how to move from being the spreadsheet user to an actuarial engineer. Here is our roadmap for the next hour. We will start by looking at the evolution of Excel, why it's not just a spreadsheet anymore. Then we will define the principle of modern Excel engineering, the core discipline we need to adopt to stop picking our application. We will move to a live demo to see precisely how to refactor a fragile spreadsheet into a robust one. And finally, we will explore the future, specifically how Python and Copilot elevate us from actuarial engineering to data scientists. Let's start at the beginning. To understand where we're going, we need to know where we came from, because the way we use Excel today is deeply rooted in its past. Well, happy 40th birthday, Excel! 40 years ago, Excel was introduced to replace the paper spreadsheet. It was designed as a simple digital ledger for sum and average. It mimics the physical world to make accountant comfortable, and for a long time, that is all it was. Well, but today, Excel has evolved into something unrecognizable to its creator. It is now a tuning complete local development platform. It is a calculation engine so powerful that Microsoft has turned Excel formula into a true functional programming language. The problem: while the tool has evolved into a Formula One car, our habits are still driving a horse and buggy. We still treat Excel like a scratch pad, not a development environment. And that is the root cause of our technical debt. While the platform modernized, our habit didn't. We still see many anti-patterns in almost every legacy actuarial workbook. First, violating dry DIY, don't repeat yourself. In software engineering, logic live in one place. In Excel, we copy and paste the same logic across 10,000 rows. That doesn't just create a large file, it creates 10,000 potential points of failure. If we find a bug, we must fix it in 10,000 places. Second, the God formula and God sheet. You all have seen that. It is the monolithic design where we put mortality, labs, reserve logic into one single cell. Well, like the formula on the right side of the slide. Or we put every calculation into one massive table. It violates the principle of modularity, making it impossible to debug. Third, obscure logic. We rely on magic number like 0.985 and cryptic reference like AB:AB. Is 0.985 a discount rate, expense loading factor, or a test rate? Well, unless you wrote it 5 minutes ago, no one knows. These habits create bad box models where critical business assumptions are hidden behind Greek coordinates. So, how do we fix this anti-pattern? We don't do it by just typing harder, to be careful. We don't do it by adding more color coding or write longer documentation that no one reads. We fix this by fundamentally changing our mindset. We need to stop treating Excel like a scratch pad and start treating it like the development environment it has become. To do that, we need to adopt software engineering discipline. We need a set of rules that force our model to be robust, readable, and auditable by design. We apply four specific rules from functional programming to our spreadsheet. First is pure function. The technical definition makes a function rely only on its input. For Excel user, the rule is pass everything explicitly. We must eliminate hidden risks by removing dependency on global name ranges or external workbook link. If a formula needs an interest rate, pass it as an argument. Second, referential transparency. This is about readability. The rule is abstract until you read like English. We need to replace cryptic Greek reference like AB:AB with semantic variable. If you can't read the formula like a sentence, it needs to be refactored. Third, function composition. This is the keyword for God formula. The rule is pipe data, don't less logic. Instead of writing one massive calculation, we build complex model by connecting small, independent, and testable Lego block function. Fourth, immutability. In modern Excel, we never overwrite data. We transform it. The rule is build train, not loop. Instead of overwriting cell to create a running balance, we use function like scan to generate a new array of value. This preserves the full audit trail and calculation history. Let's jump into this workbook. I want to show you how a small Excel formula can evolve into a maintenance nightmare. Here we have a simple setup. We have 5 columns: year, annual, month, cash flow, and present value. We have 100 years monthly cash flow. And we try to build a present value, a recursive present value formula to calculate the present value. The formula is relatively simple. We have the cash flow here. We look up the annual ways and then convert that into monthly ways, and then apply half month discount to the cash flow, and then the full month discount to the previous present value. And we need to copy and paste this formula 1200 times from the bottom up to the top. And assuming if I accidentally delete the cell or modify the cell, does the system give me an error? No, I still got a value at the top. And this is one of the probably the most dangerous silence error we get in Excel. Because we don't know about it, and we just report this number to the regulator without knowing they are garbage. So before I move away, let's fix that formula. And let's move to the next sheet. It's very simple. All we do is we add more cash flow, so we just need to create more present value calculation. The formula is identical. The only problem is we actually increase the surface area for error by 10 times because we copy and paste the formula from 1200 to 12,000 times in this worksheet. Now the requirements are getting harder. We need 5 different interest rate scenarios, and we can't just copy and paste the old formula anymore. We have to modify it to handle the 2D lookup rates. And of course, we will also copy and paste the modified formula to 60,000 cell. And if we go to the very end, we have column BO, about 67 column in this workbook. And if we look closely to this formula, what do you see? I see a wall of text. There's no indentation, no line break. It's just a long string of logic. And as this grew more complex to handle mortality, less, it will become human unreadable. And second, if you look closely, we have this double 2D lookup twice. We actually have doing the lookup twice in the same formula. And each cell will do lookup twice, and we have 60,000 cells, so we are doing this lookup 1,200 times, 120,000 times, and half of them is entirely unnecessary. We are forcing the calculation engine to do twice the work for the same result. And third, if you look at the magic number, we have 100, we have 12 here. They are dangerous for a reason you may not expect it. Coupling. Right now, 12 means everything is monthly. But what if a new product requires bi-weekly cash flow but keep monthly interest crediting? Or a mortality rate need to apply semi-monthly? Because we hard-code 12 into every part of this formula, we have locked every component to the same frequency. We cannot decouple them without rewriting 60,000 formula. We have built a model that cannot adapt to new environment or new requirement. What happens if we want to project 120 years instead of 100 years? We can't just change the setting. We must find and replace this number inside 60,000 formula. And if you miss one column, your model is inconsistent. And to be honest, this is a small workbook. We only have 67 columns. I remember one of the biggest Excel workbook I have column AIA. Go to check out how many columns that is, AIA. And I also see formula that use more than 2 lookup. They have 10 plus if statement in there. So what's wrong with this picture? It's the 4 specific thing that we've been talking about. Violating dry, don't repeat yourself. As we just saw, we are repeating calculation unnecessary inside the cell, and repeating the logic itself are causing thousands of rows. And second, the perfect jerk requirement. If you find a bug in this formula, you must fix it in one cell and then perfectly jerk it across 60,000 other cells without missing one. If you miss one column, your model is inconsistent, and you won't know until the variation is wrong. Readability. As this formula grows, it stops looking like any logic and start looking like spaghetti code. You can't audit it, you can only trust it. Fragility. This is 60,000 cells. If a single user changes a value in a cell, for example AA500, the integrity of the entire sheet is compromised. This is not just a large Excel workbook. To me, this is a minefield. Well, let's fix the problem. We're going to rebuild this model using modern engineering principle. First, we kill the magic number. I create a dedicated worksheet for our assumption, and I set up 2 variables here. One is called period per year, the other one is projection years. And if we switch to quarterly projection or extend the projection years to 120, we change it once here. and it will propagate everywhere. And I also add two worksheets for input annual rates and cash flow. And each worksheet have a table. This one is called table end rate, and this one is called table cash flow. And we convert the Excel range into Excel table with proper name. So our formula will no longer say :2 to A2 F102. They will say table end rate. We are killing the cryptic reference using this table. And third, we're going to kill the graph formula using function composition. We broke the logic into small testable Lego board, what we call helper function. And if we click on the link manager here, we see we have FN rate, which do the two-dimension lookup to get the annual rate, and then we have the monthly factor that convert the annual interest rate into monthly discount factor. And of course, we have the core calculation to apply the discount factor, the half-month discount factor to cash flow, and the next period with the full month discount factor. Well, and let's look at a primary logic function, period step. I don't know about you, but I can't read the formula myself in the link manager. So I'm going to jump to advanced formula environments in Excel, which you can download from Microsoft website. So inside the period step, this is AFE, and you can see it's much easier to read the formula. Inside the period step, we're using the left function to assemble different pieces. We using underscore year to store the value from return from function year, and underscore rate to store the return value result from function rate. And finally, we have the factor that return from the fn month factor function, and then we pass the value into the PV core function. This solves the drive violation. Don't repeat yourself. We calculate the lookup once, store it into a variable, and reuse it. And we have successfully refactored the component. Now, the next step, we are going to eliminate the recursive formulas that we saw here. So we build a building block function called PV stat, and let's look at the other Excel workbook, PV total. They are the same, except this one we have 1,200 rows per column, but this one here we only have the final result. In the old world, we probably still have to build that 1,200 rows somewhere, hide the seed and link the total, and it's quite messy. In the new world, we wrap the loop into the function itself. And if we read the formula here, it's actually quite easy to understand. We calculate the present value using cash flow 1 and the scenario rate prompt by AG1. And let's look under the hood at PV total. This function introduces a very important lambda function called reduce. And we also build a reverse index that count backward from 1200 down to 1. This tells Excel that we are working purely in reverse time, which match our original actuarial logic. And the reduce function is actually the for loop of the modern Excel. It starts at 0 and iterate through our reverse index. And the function composition here is inside the loop. We are actually calling the PV step. This is the legal bot that we build and we test it. We don't need to rewrite any discounting logic or mid-month adjustment. We just call PV step. And in the future, if PV step need to modify or fix a bug, PV total will just update automatically. We have a single source of truth for the logic and a flexible engine for the loop. And maybe let's stop here and go back to look at the reduce in a little bit more detail because this is the first time we are seeing it. For those who use VBA, we're using for loop to calculate running total. And we create a variable, let's say called total, and we set total equals 0 before we go into the loop. And inside the loop, we go through each row and set total equal total plus value. Reduce is the functional programming version of that loop. It takes 3 arguments. The starter, this is the starter value, 0. We do that in the for loop as well. We assign total equals 0. And then we have the reverse index here, the iterator. We are looping from 1200 down to 1. And then that is the logic, the lambda. Inside the lambda function, we have 2 major variables. The next PV, what we call the accumulator, the total, the value carry over from PV step. And I is the current item, start from 1200 and then -1 based on the reverse index that we pass it into. So in simple English, the formula says start at 0, working backward full time. At every step, take the PV users calculate, the next PV, combine it with the current cash flow at time I, and hand it to PV step. It handle all the state management for you. You don't need to declare variable or manage memory. You just define the transition rule and reduce will handle the logic for us. So we replace the requested formula. We don't need 1200 row for each result. But I don't know about you. I still have a problem. I still have to copy this formula 5 times, 10 times, 50 times. And if we need to increase scenario or add more cash flow, we need to modify this formula. Can we do better? I'm a lazy guy. I keep telling people, can we generate the entire sensitivity grid dynamically? Of course. Let's go to the next version, PV matrix. One single formula. This is only one single formula here. We pass the whole cash flow and the whole annual rate. And it returns a 5 times 10 dynamic array with the patient value that we want to see. So how we do it? Let's look at the function. And this time we are using a make array. We make a array by number of cash flow and number of scenario. And inside this make array, we call a lambda function. And that lambda function, again, it will call the building block that we create in the previous exercise, PV total. And we pass the corresponding cash flow and scenario into PV total. And it will return the PV value to the corresponding cell. And once we do 5 times 10, 50 patient value, it will return the dynamic arrays into Excel. So we just replace 60,000 fragile formula with 3 robust functions, PV step, PV total, and PV matrix. We eliminate copy and paste. We have 0 magic number, and we have total audibility. That's what it meant to be an actuarial engineer. So we have this dynamic array of number for PV matrix. It's fast and robust, but there's one important thing missing, the context. What are those numbers? A grid of number without label is dangerous. Which column is scenario 1? Which row is cash flow 7? In the old day, we could manually add this header in row 1 and column A. But if the data shift, your label could be wrong. And that's why we create the report function, PV report function, with the proper header. So when we look at the PV report logic, again, it's going to call a function that we already built. So we create a data grid using PV matrix. And then we create a header from cash flow table and transpose them from horizontal to vertical. And we using vstat and hstat. They are we using hstat to combine the row label to the left of the data grid, and we using the vstat to combine the scenario header on top of the result. And that is what we see on the Excel table. So we have a fully dynamic label report generated by the code. And if I rename any way 1 to sort up or sort down or whatever more meaningful in the source table, this report updates instantly. And if I want to add another 20 cash flow, the report automatically grows. The calculation logic, the PV step, is decoupled from the loop PV total. And PV total is decoupled from the layout PV report. This is what we call modular design. This is the real actuarial engineering. We have built a powerful engine, but right now, the engine is trapped inside this Excel workbook. Well, I create a new Excel workbook and I try to call the PV report. And you can see it returned an error. Why error? Excel is virtually screaming at me and say, hey, I have no idea what this function is. And if I go to the formula and go to link manager, well, there's no lambda function here. So that is why Excel is complaining. And it's a simple fix. All we have to do is go to GitHub. As I told you, I store uh, all the logic in GitHub. And we can import the logic from GitHub here. And boom, you see they actually return the result now. And we go back to the link manager. All the lambda function has been populated from GitHub. However, there's a catch because the Excel workbook doesn't talk to the GitHub automatically. We have to come in here and enter the GitHub git URL to import the logic. So if I update the GitHub logic, the Excel workbook doesn't know about it. And the worst part is I may have more than one Excel workbook. I may have 50 or even 100 Excel workbook calling this library. And every time I change that, does it mean I have to import the logic 50, 100, or even 1,000 times? And how do I make sure that I'm using the latest version of logic? I mean, do I have to load the Git logic from GitHub every time I open the Excel workbook? I mean, that is problematic. So one of the solutions is using Excel add-in. Let's delete all the lambda function again. You can see I have the same error. But if I go to the next worksheet without any lambda function, I'm still able to produce the value. How? Because I actually store all the logic inside a Excel add-in, and I already enable the Excel add-in in my Excel. So every time I open Excel, it will actually automatically load this add-in to Excel as part of the Excel function. And that's why when I call the function actuarial underscore PV library Excel AM and then start with PV reports, it actually returns the value. Even I don't have to import the LAMBDA function. However, that causing another problem, and I have to warn you using this approach. With great power comes great responsibility. This approach requires strict software engineering discipline. Imagine I release a new version of add-in without proper QA testing. Suddenly, every single Excel workbook in my company that depends on this add-in will break at the same time. And it probably will make it worse if this happened 2 days before the year-end close. That's why we can't just be Excel user anymore. If we want to build shared library, we must adopt the testing, version, and QA of real software engineering. And another vision I have, why people like Python so much? Because for data scientists, there are a lot of open source library shared for them. They don't have to write the library themselves. They just load the library and call the function. With what we have here today, we can store the logic in GitHub and we can create Excel add-in. Do you think one day we will have an open source actuarial ecosystem based on Excel? We, as an actuary, if we want to using an IFRS calculator, we no longer need to develop everything from scratch. We can just download the add-in and then we can start using it. And if we find some feature that is not available and we want to extend it, we go to GitHub, we modify the logic, we rebuild the Excel add-in. The next guy who download the library will have the feature that you put in. I don't know if that is a gym or something that reasonable. We can see that in couple years. But if people, data scientists can do that using Python, why can't actually do that with Excel, with LAMBDA function, with GitHub, with Excel add-in? Well, we have reached the end of the first half of our journey. Let's take a quick look at what we have achieved today. We have replaced fragility with reliability. We killed the God formula and the anti-pattern, transforming our spreadsheet into robust, auditable code base using LAMBDA and functional programming. We enable scalability. We move our logic out of individual cell into modular function. Open the door for industry-wide collaboration using GitHub, Git, and add-in. We are no longer spreadsheet user. We are actuarial software engineers who build systems. But engineering is always about choosing the right tools for the right job. Is modern Excel the answer for every single task? No. Excel still has limits on scale and statistical capacity. We can't run machine learning model on hundreds of millions of rows inside a spreadsheet. To complete our transformation and become a true data scientist, we need a pathway to powerful external tools. And that leads us to the next evolution, integrating Python into our Excel workflow. Now I want to address the elephant in the room. Microsoft announced Python in Excel about 2 years ago. And I was so excited and jumped right onto it. For about 24 hours. I think it's less than 24 hours because I find out that Python in Excel has serious limits. First, Python in Excel have to run on the cloud, not my own desktop. And second, to do with the first one is they have computation quota. And I think I reached the quota within the first 24 hours. That's why I learned about the limits. And the third one is it has 100 met data capped. You cannot analyze data over 100 met. The last one, and probably is the most important one, is it only support a limited set of open source library. They are very popular, they are very powerful. However, you can only use whatever library that Microsoft provide. So I gave up. I mean, I'm using Visual Studio for Python. I have my own library. I'm not going to move to Excel to run Python when it's actually not as good as what I have. And after a while, I think I realized that Python Excel is not for people like me. Python in Excel is mainly for Power Excel user. Power Excel user who actually reached the limit of Excel and they are looking for something more powerful so that they can do more analysis on the data. Then you may ask, well, if that's the case, why don't you jump directly to Python using Visual Studio or Database? I think the answer is fiction. For Actuary, the most challenging part of learning Python is not the syntax, it's the setup. It's fighting IT for administration right to install the software necessary for Python, to manage the environment and even figure out where to load the data. Think of Python in Excel as the stepping stone. We can focus on the logic, not IT. We learn how to think in data frame, which are superpower Excel table, without spending a single minute on installation. And even the limit that I mentioned maybe is a good feature, a feature that reminds us that we graduate as a experienced Python developer. Because by the time we need to work with more than 100 meg of data or use up the computation quota, I think they are sending a message to us that it's time you should think about moving your Python program to enterprise platform like Visual Studio or Database. And the good thing is, all the Python experience, the Panda code that you wrote is standard Python. When you eventually outgrow Excel or Python in Excel, and I'm sure all of you will, you can copy and paste the logic directly to Database or Visual Studio. We are not learning a toy language. We are learning the industrial standard, only inside the tools that we already know, Excel. And another thing I want to make clear, I'm not suggesting we get rid of Excel. That is never my intent. Excel is very powerful, very useful, and it will be part of it will always be part of our actuarial toolbox. But I want you to look at this table and use this table to map our Excel experience into a stronger engine. Think of this table as our Rosetta Stone. We already know the concept. We just need a tool that supercharge us. Say for example, if you know VLOOKUP, you already know the concept of pandas. If you know solver, you know what to do with SciPy. And if you use trace persistence in Excel, you are ready for level X. Before we build complex model or sophisticated data visualization, we need to understand how we can import data into Python in Excel. Remember, I just mentioned Python Excel is using standard Python, except one minor thing, the input. When we load the data to Python to Excel, the data must be sitting inside Excel. We cannot using CSV or database directly in Python in Excel. Say for example, we have data in column A and column B, year and premium. We using the XL function. This is probably the only function in Python in Excel that is not standardized. We use this to load data into Python in Excel, into a data frame. And once the data is in the data frame, then we can do whatever we want. And for this example, we want to sum the total, which is 3,700. And apart from using the cryptic reference, column A, column B, we can using the range name as well. So we have a range name called discount rate here, and you can see we can refer to it and we output the value. Or you can hard code the data inside Python in Excel, and you can output the table as a array to Excel. Well, not sometimes, we probably do that very often. We need to get data from a CSV from database. So we cannot use Python in Excel. Well, not really, because in Excel, we have a very powerful tool called Power Query, and you can actually load CSV, database, PDF, even data on website using Power Query. And once we set up the Power Query, even this one is connection only, we actually haven't loaded the data into Excel. We can actually set up the Python program to refer to this Power Query, and it will return all the data that connected by this Power Query. Actually, it's over 400,000 records here. So we know how to get data in. Now let's see what we can see in Python in Excel. Excel is great for pie chart or other standard chart, but actually often need more powerful or sophisticated statistical chart. I'm going to quickly go through 5 examples to show you how Python in Excel can provide impressive chart for us. The first one is the violin plot. A violin plot is good to show us the full distribution density. And if you look at the code, this is one single line of code. Once we load the data, we just call the corresponding function that plot the violin plot for us. And the second one, this is my favorite. I want to see how every variable correlate with each other. I can do in Excel, I can create, I don't know how many scatter plots I want, but I can create them manually. But again, Python in Excel, one single line, we specify the PyPlot function. And the next one is joyplot. This combines a scatter plot with histogram on assets. It led us to see the individual data point and their marginal distribution at the same time. Again, Very simple function to call once we load the data in. The next one is the heat map. I will call that my second favorite. We probably use conditional format in Excel today, but uh, Python and Excel allow us to have better control on the color, uh, and again, it's just one single line of code. The last one is the density plot. Um, it's a smooth probability density function curve. For Actuarial, try to fit a distribution to raw data. This is the first step in our analysis. I guess the key thing I want to show you all these Python programs is they are all really small, really simple. We don't need to write hundred or even thousand of lines in here. In most cases, it's less than 10 lines of code. And we can replacing manual charting with uh, programming visualization or scripting visualization. Now, we can see how we can see data in Python. We can look for how we can using Python to solve data. The first one is solver. Uh, I'm sure we're using GoSeed or solver in Excel before. This one, again, we can do that in GoSeed. We have a future value, we have number year, we have the present value, and we want to find out the discount rate. Again, if we look at uh, the solver here, we just define the input data, we define the function, and then with one single line, fsolve, it will solve the value for us. And the next one is, assume we have three different assets, and we have the correlation matrix for equity, real estate, and bond. And the correlation is 0.6, 0.2, and 0.1. And we want to build a simple ESG, economic stochastic generator, that makes sure these three assets are randomly produced, but matching the correlation matrix that we define here. And again, once we load the data, it's one single line, and we got the value we want. And I even actually, after I got the result, I compare the correlation with the input. So I compare column O with column P with column Q, and column O with column Q. You see it's 0.6, 0.12, and 0.22 compared to the matrix that we define, 0.6, 0.2, and 0.1. Not too bad. And the last one is a curve interpolation. We have a yield curve. We have four data points here: year 1, year 5, year 10, and year 30. And we want to get the target the target yield for year 17. And again, once we know the data, the key thing is we know the function to call, cubic spin, and we got the result we look for. So what we have seen so far, I show how to using Power Query to load data in Python. We show some fantastic visualization using the scientific chart, and we also do some mathematic calculation using solver, simulation, and interpolation. We no longer using Excel. We are actually running a scientific computing environment inside Excel. The beauty of this is it actually scale. Today we may run 10,000 row for some kind of analysis. Tomorrow we may have 100 million record, and that go beyond the compute quota or the data size requirement. But we don't have to worry because we are using the same Python logic. All we need to do is copy that piece of logic, change the input source, and pass it to database or other enterprise environments, and you will be able to reuse your data. So, so far we fixed our formula. We have upgraded to Python, but there's one more technology that we cannot ignore. The question that everybody asks today: will AI take our job? Will AI replace actuary? I think the simple answer is no. But an actuary who uses AI can have very good chance to replace one who doesn't. And the same logic apply to our software. Software integrate with AI will replace software that isn't. We need to stop thinking AI is a fad and start considering it as our junior analyst. So why does AI matter specifically inside Excel? Well, I guess most actually are heavy Excel user, and also Excel is very complex. We just spent 40 minutes talking about LAMBDA, Python. There's a lot to learn, and Copilot can be our teacher. Copilot can bridge the skill gap and allow us to using this advanced feature before, before we can fully master the syntax. And it will turn the natural language into programming. Let me show you 3 specific ways Copilot accelerate the actuarial engineering workflow that we just discussed. The first one is legacy code translator. Remember the graph formula from the beginning? We can highlight a massive unreadable cell and ask Copilot, explain this formula to me step by step. It will become a documentation engine for legacy formula. Second, the Python writer. Remember the Python code? We're probably not familiar with every single function in the Python library, but we can just type what we want and ask Copilot to generate the logic and execute it for us. Copilot will write the Python code for us and is a perfect tutor. We can keep asking Copilot to explain the logic for us as well. The last one, the data analyst. We can ask Copilot to highlight all the policy where the loss ratio is above 80% and is in Northeast Canada. You will apply the conditional formatting instantly. We don't need to do anything about it. But like Python, we have to using AI with discipline. AI can hallucinate. It can write a formula that looks right, but produce the wrong result. As actuary, our professional skepticism is our greatest asset here. We should never trust blindly. Always review the code and the result. Validate the output. Copilot is a powerful engine, but remember, we are the driver. There are many AI features in Excel. Most of them you can access from this Copilot function, but there are a couple of them hiding somewhere. One is the data. We have a key data feature here, and it's also powered by Copilot. The other one is the finance icons here. It's an add-in, and it can do a lot of AI function for me, especially on the financial side. But let's go back to Copilot. Copilot have 2 main functions here, a app skill. So In the Copilot skill, we can ask it to suggest a formula or create a pivot table or generate some insight using Python. There are many features that we can use with Copilot skill. But we want to focus on the agent mode. It's a new feature um, that Microsoft just recently introduced. I think it's less than 2 weeks that they introduced this new feature. And before we start talking about the agent mode, I want you to understand the power of agent mode is we actually allow it to work on our Excel workbook and it will create very useful analysis or Excel table for us. However, I strongly recommend us save the Excel workbook before we engage agent mode. We never know what it will do. So always better to have a backup. And once we start the agent mode, you can see that we actually can choose what AI model we can use. And as a matter of fact, that is what I've been doing. I compare the two models and see what they produce. Do they produce consistent result? So I actually asked both AI model, GPT and Cloud to generate a discount cash flow model for me. And the one, this one here is generated by ChatGPT. And I didn't write any formula. Everything is prepared by ChatGPT. It actually generate the input table here, and it do the detailed calculation here, and it generate the table for me. We have a discount rate and a growth rate. So discount rate is 8%, 10%, and 12%. The growth rate is 10, 15, 20%. And that is the present value of the what they call the enterprise value, which is the present value plus the present value of terminal value here. So we got the value we want from ChatGPT. And I asked the same thing from Cloud as well. And also it produced similar value here. They call it enterprise value, but in a different format. So we have discount rate, we have growth rates here. But if we compare these two models, the result that generated by these two models, the middle one is what we start with, 10% discount rate and 15% growth rate. It's 31 million here. And we also got the same value. But if we look at the other scenario, we have 8% discount rate and 15% growth rate. So 8% discount rate and 15% growth rate. This one is $32 million, whereas this one is $51 million. So although both of them provide a very fancy report, the key is we have to validate the value. And even just compare the result from the two model, they are not the same. So we have to be careful. And I actually review the result and I find the result from ChatGPT is correct. But that is the point I want to make. AI agent or any AI, they can provide something. When you look at it, you think, oh, that's great. We have the value, and it makes sense. You have to go through detail and looking at the result. And the next demo is I want to do analysis. So I download 3 Canadian insurance company financial result from OSFI. And I just asked the Copilot agent mode to do the analysis for me. And you can see that this is from County, and it generate again many report for us. And for those who are IFRS 17 experts, I'm sure you will find this interesting. But if we look at the other one, the other reports, this one is the same input data. I download the data from OSFI, and that is what GPT gave me. And you can see even the chart they provide actually cover the data. But I think this is only the beginning of rolling out agent. I think this is just teething problem, and as time go by, I'm sure Microsoft will fine tune it and will have better result. We have covered a massive amount of information today. First, we talk about discipline. We saw how to tackle a fragile 60,000 cell spreadsheet and refactor it into a robust auditable system using LAMBDA and functional programming. And we stop copying formula and start importing code. Second, we unlock the power. We using Python in Excel act as a stepping stone, allow us to replace manual chart and messy VBA with professional-grade data scientist tools like Pandas and SciPy. Last, we embrace the future. We look at how Copilot and open source library allow us to stop computing on the math of interpolation and start computing on the strategy. The next question is, the tool has evolved. We have LAMBDA, we have Python, we have Copilot. The question is, how about us? Have we evolved? Excel is at 40. It's no longer just a digital ledger. It's a tuning complete development platform. It's time for us to stop acting like a reactive spreadsheet user and start building like a proactive actuarial software engineering. Thank you for your time.